All right, hello and welcome. This is lecture 1.2, the same topic as we have already discussed, the nature of econometrics and economic data. And so now we are just having several points on the two-variable regression analysis. All right, so let me show you full screen. Full screen mode. Okay, so here are some data on weekly family income, and you can see that there is two variables, obviously y and x, and the pair regression analysis involves just the dependent and independent variables. So dependent variable is our weekly family consumption expenditure in dollars, and X is just the family income. So these whole people represents the population, the so-called population. Of course, we know that there are many families, but we have only gathered data on 60 of them, and we presented those findings in tables. And the table consists of 10 groups. So we divided all the families into 10 groups in consumption, starting from $80 to $260 per week. We also calculated totals, just the sum of those columns, and we calculated the mean. So divided 325 by the sum of the first column, we got 65, and did the same for all of the 10 columns, and got our conditional means. What does it mean, conditional means or conditional expected values? Mean and expected value is the same as just the what will be y given x. So to read this, or to read this formula, we just what will be first variable given. So this vertical line just represents given x, and what will be consumption given the family income is 200. The conditional mean will be 137. So we are expecting that the family whose income is like that will consume $187. All right, so this information, what is important actually here are those conditional means. And if we place this information into the graph, having those dots as the conditional values, so here they are, and the rest points that we have measured. So for example, in the group of 80, we can see that the points started slightly above 50 and ended above that conditional mean. So let me show once again. So they are starting with 55 and ending with 75, 55 and 75 over here. The same kind of information we place around all those points, around all those 10 groups, and just select conditional means. And if we draw a line through those conditional means, this line will be actually the regression line. So nothing more. We just try to find those conditional means. What will be, again, what will be y given x? What will be y given x? And if we can answer this question using just the simple calculation of mean value of the average value in another term, then we can find the regression line. Okay, so this is quite straightforward. Now, what is unconditional expected value of weekly consumption expenditure? How can we calculate unconditional? So those points are conditional means, right? Those both points. But unconditional. What do you understand? How can you understand? This is the formula. Expected value of y. Here's the smallest value. Here's the largest value. We can sum up and find the average of all those values. So this will be the average value of y. All right? The same kind of thing we can do in the table. We can just find the totals. We can see this group of totals. If we sum those totals all together, divide by 60, number of observations, here will be expected value of y. And I believe it will be around 120 something. Why? Because by definition, each regression line must go through the point expected value of y, expected value of x. So somewhere here will be the expected value of y, and somewhere here will be expected value of x. So it always comes through this point. And just by looking at the regression line, you can see that somewhere in the middle there is the average value. All right. All right. So the same kind of thing we can do. Just look at the first group. The first group. It starts from 55 and ends with 75. We actually virtually place all those points over here. And what does it mean? What does bell-shaped curve mean? It actually means the probability density function, or PDF. And this probability density function just measures what will be the expected value around the mean. So we try to measure what will be the probability that the value will be slightly higher than 65, and what will be the probability of slightly lower than 65. We can see that a lot of probability comes in this shape. What will be the probability of 149? And we can see that those values are declining, declining, declining. There might be very, very small chance to have the value of 149 consumption, given that the family income is 80. Very small. The same kind of thing happens in the low-hand side. There is very, very unlikely that we meet something around 20 consumption with the family income of 80. The same kind of thing happening all the way through the points. And so let's say we take this consumption expenditure of 220, we can see that the average is 149, so we can expect that around this kind of square, around the bell-shaped curve, we can meet the majority of consumption expenditures. And it's highly unlikely that the family who earns that much will spend around 65. So nothing more, these are just probability density functions. So probability, what is how probable is that we meet some value. Okay, probability density. All right, so this kind of regression line is the population regression line. So now the population is 60 families. Of course, we know that they are much more than 60 families in the country, in the world, but we are given this kind of population, and we are trying to estimate the equation around those 60 families. Okay, next I'm just reminding you what we already met in the previous week. The meaning of the term linear. So what we are caring for is linearity in parameters. There are two types of linearities, linearity in parameters and linearity in vectors. What are parameters? Parameters are those beta things, beta 1, beta 2, beta 3, and so on. These are parameters of the function. Those are just numbers that we are going to estimate. What are y? Y is a dependent variable, beta consumption. What is x? X is the weekly income, and x squared may be the square root of this weekly income. And we know that the kind of formula that we get is a parabolic or quadratic formula in the first graph, but this is a linear function in parameters, in betas. Although it's not non-linear in x's, but it's linear in betas. The same kind of thing happening here. Is it linear or non-linear? It is linear in betas because betas are in the form of a line here, and actually we can linearize this equation just by taking the logarithms. Log of y will be just beta 1 plus beta 2x. Okay, so the only thing which changes, log appears in front of y and exponent disappears. And betas become linear. The same kind of thing happening over here. We can see that each beta is just unmodified. It's just stated like this, and the function is linear in parameters. So all those functions you can estimate easily with linear regression analysis. You can see that the variety of different equations, but if you are placing those betas linear, you can estimate linear regression function. Actually, in further weeks, maybe we will touch nonlinear regression, where there is special kind of violation of assumption of linearity, where betas can be nonlinear, and we also have the mathematical methods to estimate those functions. All right, but for now, just we say that all linear regression functions are linear in parameters. Next thing that we are taking care of is UI. UI is the vector inside the regression model that captures all variation that goes besides the factors that are included in the model. So everything that you wanted to estimate but you simply don't have information about, for example, consumption and income. So X is income. But besides income, you might see how large is your family, for example, the factor of the family size or the place where the family lives, and other factors. All those factors that you have just not included in the regression equation, they go to the UI. And UI is the difference. Well, let's have a look at the first formula. It is the difference between the actual observation and the value that, the conditional value, right? So actual observation and the expected value of y. Each time you will see different values of ui's. Moreover, if we are talking about the true regression line, we might not know what will be true value. What will be the true value? And we can only estimate those ui. To some extent, it will be estimated. We will get the error of the regression, and this error of the regression will be called UI hat. Later on, I'll show you the graph of where you can see what's the difference between UI and UI hat. UI hat means just the so-called symbol on top of U. All right, very nice assumption which takes from this formula. Actually, what is the yi, right? So yi is the difference between not the yi. What is this expected value of y given xi? This thing in the first right-hand side part of the equation. What is this? It's just the difference between yi and ui. And actually, this thing, expected value of y given xi, and this thing, expected value yi xi, it might be the same, and essentially it is the same. And if it is the same, so this part and this part are the same, only if the expected value of ui is 0, only in this term. So we just say, all right, everything that we are not included inside the regression equation is just 0. And we estimate our regression equation later on and got some difference between the line and the true value. There will be some values. Here's the regression equation. Here's the difference between the line and the value. And those things will be called UI hat, the error of UI. It's normal. We cannot draw a line through all the points inside our data. If we do so, the actual line will be non-linear, but it will be the polynomial of n minus 1 order. So for example, if we have like 3 points, we can use the quadratic equation to estimate everything perfectly. But what if the next point will be here? And the error between these points, the prediction of our equation and this point will be very, very large. So we cannot do so. We try to minimize the distance between the line and the points, the distance. Actually, OLS, the ordinary least squares, the method that we have mentioned in the previous lecture, measures the distance squared between the line and the points. So we sum all the distances, we square them, and find out the minimum of that. All right, so what is UI and why it appears here? So for example, the vagueness of theory, what can we say about the vagueness of theory? We actually don't know the, hold on. We actually don't know for sure whether the income actually is the predictor of consumption. We don't know that for sure. We may not know how one variable impacts another in economic terms. We see this impact, but this impact might not be true. It might be of the result of the combination of other factors. And availability of data, that's what we talked about. So all other factors that we are not including inside the equation just go to this UI term. Core versus peripheral variables. Sometimes we think that besides income, family size also impacts that. It might be core variable if the regression becomes better. How do we understand why it becomes better? Because we measure the quality of the regression, we measure the standard error of regression, we measure the coefficient of determination, so-called R squared, which measures how much variation explains in comparison to the total variation. If we see that the quality of regression grows, then it might be core variable. Sometimes when we include many variables, like besides that the marital status, race, nationality, any other variables, maybe the profession, some of the factors that we are included might be considered as peripheral variables. Altogether they have some impact, but one by one they do not have any impact. So we cannot distinguish with that. And we are okay with that because we know there's a special UI term which just captures all those bumps and ups and downs in our variables. Intrinsic randomness and human behavior. So let me have a look. What do we mean? So if we succeeded to introduce in all the relevance, there is bound to be some randomness in individual Y. So actually, we might just by chance meet the sample which stands out of the normal way of things, which is just selected by chance, which doesn't follow this pattern. And we cannot avoid that when we say it is intrinsic randomness of human behavior. Sometimes maybe those families in the sample, they know something about the future. For example, they expect that they move out from the country to a vacation, and they spend much more than regularly they spend. So you can see that we cannot know the human behavior, and we just are okay with that. All right, poor proxy variables, and here's the example inside the brackets. Instead of permanent consumption, we use consumption. Instead of permanent income, we use income, and so on. So sometimes we don't know the actual value, or this value is not measurable in economics, in macroeconomics, so we're sticking with what we have. All right, and of course, run functional form. It also is very common thing that we think the equation should be quadratic, but it actually not quadratic. It's something different. All right, so just we say that UI term presents, and we are okay with it. Now here, what we can see on this graph. The bold line represents the population regression function, PRF, population regression function. It's just the value of beta 1 plus beta 2 xi. So this is the expected value of y given xi. So if we measure here, we got the value, which is the average. And at the same point, we estimated different sample regression function, SRF, sample regression function, yi hat, beta 1 hat plus beta 2 hat xi. And this function has systematic overestimate on top of the population regression line. So each point starting from point A to the right-hand side systematically overestimates the population regression line. And we can see that here is the point, yi, the actual point. Here's the expected value. And the regression goes through the point yi hat. So it estimated the consumption, estimated the consumption and measured it equals to yi hat. So the difference between the estimated line and the true value is this, ui hat. But the difference between the actual value and the average value is ui. So yi hat is actually smaller in this particular example, in this graph. Y hat is smaller, and there is some value which just left the difference between the sample regression function and the population regression function. We don't know population regression function for sure, because if we look at the not 60 families but more families, our 60 families appears to be another just a sample of the true population. But given different types of data, if let's say 60 is our population, we take some parts of the data and estimate the regression equations, they will be just linear functions, and they might fluctuate a little bit given different parts of data from the population. And this is normal, and actually we stick with what we see. Sometimes those regressions are overestimated, and sometimes they are underestimated, the true population line. Again, no matter how we estimate it, if we use OLS and we met all our assumptions, the linearity, there is correlation between y and x actually, and this correlation is pretty high, and there are no correlation between x's, between xy and xj, different factors. There is zero correlation between ui and the factors. Normally distributed residuals after we estimated regression. We see that there are no multicollinearity, so the correlation between xi and xj is low. There are no heteroscedasticity, no patterns in our UIs. And so these are all assumptions of Gauss-Markov theory. If we met all of them, then we can see that the sample regression functions that we estimated, or population regression functions that we estimated, they are best. So those betas, those parameters of regression are blue, best, linear, unbiased. right? And these are parameters best in the class of linear estimators. So all other methods which brings us linear parameters, they will be not better than those which are estimated by OLS. So here are just some points that we needed to place some attention here, and altogether lecture 1 and this part of the lecture, they should be considered as the single one. All right, so here we just talked about two variable regression analysis, very common technique. Now let's, do we have any questions? All right, so here we have some questions stated in the in-class practice, so let's open them and try to answer them. Hold on. Okay. All right, so what's happening? Okay, so cannot close. All right. What is the conditional expectation function or the population regression function? Again, have a little think. How can we distinguish between conditional expectation function or population regression function? First of all, is it the same or not? Conditional expectation function and population regression function, is it the same or not? Yes, it is the same. Okay, so now can you define what is population regression function? Can you define what does it mean? So when we talk about population, actually we talk about the true relationship between dependent and independent variables in a population. And in other words, it indicates the expected value of y given specific values of independent variables. Right, so if we look here, strangely it refuses to open, so let me, yeah, okay. So this is our population regression equation. So it goes through conditional values. Each point is the conditional value, right? So now, what is conditional expectation function of the population regression? It is the theoretical construct that defines the true relationship between dependent and independent variables. Okay. Next, what is the difference between population and sample regression? What can we see? Here is our PRF, population regression function, and SRF, sample regression function. What is the difference? What did we just heard about population regression function?
How do you understand population and sample? What is larger? What is larger, population or sample? Yes, we take sample from population. So we can divide population into an infinite number of samples actually. If the population is very big, but for example, if we have 10 values or 60 values like in our example, we can have 59, population of 59, and we have different permutations of those 59s, and this will be a sample. Or we can take just 10 points out of 60 with different points randomly selected, and they will be samples. Okay, so population regression is actually the true value. So we measure those conditional values. Each point is conditional value of y given x. What is sample? We just fake a little bit. And sample regression function can be considered as population regression function, but just given some part of the values, right? So the difference is in that it is, first of all, it is estimated using the sample based on our observed data, and sample estimates are prone to sampling error. So we might just select the point, so that the regression, sample regression might go upper than the population regression, or if we select different values, it might go over here even with the different slope. It really distinguishes the sampling error. That's why sometimes it is necessary to select different samples, maybe 3 or 5 times, and then estimate regression equations using those samples and then average them. These are parts of machine learning. It is called the cross-validation. Sometimes we can leave just one observation out, re-estimate, and then just average all our values. Or we can use parts of the samples. So, for example, take third out of the sample, re-estimate, and make it several times, and then get the result. All right. So here is the difference between population and the sample. Next one, what is the role of UI? What is the role of UI? What's the difference between the stochastic error term and the residual UI? Here should be UI hat actually. What's the difference between UI and UI hat? Okay, let's have a look at what is UI. UI is the difference between the true value and the estimated value, the conditional value, right? So this is the difference. Why it happened? Because there is some random variation in the dependent variable, and UI actually can be placed in different parts. So it can be higher than conditional, it can be lower than conditional. And to estimate this variation, we use probability density functions. We just show what is the likelihood of meeting the point which is in this part or in this part. Okay, so around conditional mean there is certain variation of yi. So yi, not the yi, UI, this stochastic error term, it just captures this random variation around dependent variable that is not explained by the model. And the residual, it is the observed error. So here was our yi. Here's the estimated value, yi hat. The difference between the true value and the estimated value is the error term. So ui hat is just the error of the regression. All right. So do you understand? What is UI? UI just captures the variation in dependent variable. So we measure consumption, the variation in consumption. The residual of the regression model is the difference. So we estimated the regression model. We have this equation. We place this equation on the graph. Here it is, the sample regression function. And the difference between the true value of yi, so the family which income is xi, consumes yi dollars. For example, 150. And our regression estimated that it consumes 140. So this is the $10 difference is our error of regression. But on average, family with consumption, with income xi, it consumes 120, for example. But this particular family, yi, consumes 150. And the difference between the on average consumption, 130, and this particular family, 150, is just this 150 minus 120, right? $30. But the regression estimated higher than the true line, but closer to those particular family. If we haven't selected this particular family, maybe this family is just an outlier. Maybe all other families, they are consuming slightly more than 120. We don't know that. But what if? And if the point was over here, let's say over here, and the regression is higher than this point, so the UI hat will be the difference, the error of our estimated value, and the observable value, our observation, and the estimation. All right, so two differences. Variation is like that, highly unlikely, but it is true. Our estimation is like that, and this is the error between the line and the true value. All right, so next question, why do we need? How do you understand that? How do you understand? Why do we need regression analysis? So the second question actually helps us answer the first one. Why not simply use mean value of the regressant as its best value? Okay, let's have a look. The mean value of regressant. It will be somewhere the mean value of all those values, right? And the mean value will be around 120. But here we can see that given some conditions, our 120 average will be quite different. It might be a lot low or somewhat high than that. So we try to gain much more from the data. First of all, we have 10 income groups. Instead of the single value, we already have several points. We know what will be the expected value given each of those points. We actually can select somewhere in between. So for example, we can select 190. We don't have the observations here, but if we build the regression line, we see that this is our weekly consumption expectation, somewhere here, right? Somewhere in between the consumption expectation of 118 and 200. So this is the benefit of using linear regression. It is just the line. We can select any point here. Inside, here's the smallest value of 80, and here's the highest point of 260. We can select any point in between. And if we select any point in between around the mean, so if we expect that the mean is over here, for example, from 155 to 165, so here will be the smallest error. So if we select the point, let's say this one, or the point this one, the error will be smallest. So because let's see it, do we have any options to edit? No, we don't. All right, so the actual thing is, these are the points. Let me draw several points. Here's the regression line, which goes maybe close to the points, slightly below, slightly above, but it does not cross any of the points actually. Here's the mean average value. Here's the mean average value of y. So around those values, in one standard deviation, we expect to have the lowest confidence interval. So all the points around the mean will go in the smallest range. So our prediction or our forecast will be much more accurate around the mean. But if we select the point which goes on the left-hand side around 80, we might have larger variation. We might have even larger variation if we have weekly income of 260. It is true because these are economic variables, and by definition, the larger you have the money, the more variance you have. But in consumption. But let's say that we're talking about some different variables, maybe some physics law, and on the edges there will be much higher variation. And by definition, around the mean it will be smaller variation. One thing which we also might mention is here's the starting point of 80, and here's the ending point of 160. We cannot select any of the points below and above those intervals. They are out of the sample. We don't know the law. We know the law just based on the sample that we have had previously. We have had 80 and 260. If we have selected 300, it might be, but the variation might be different. Maybe the so-called the law might be different. It might not be linear. It might go like that in exponential thing, or it may go like that in the logarithmic thing, for example. Right. So it's just the precaution that we must use the regression line that we just estimated only for predictions inside the sample. It's normal to select like 82, 83, 80, 89, those points that we do not have, but it's not normal to select any of the points like 70, which goes below our 80, the initial point. Okay, so a linear regression is just a linear relationship, and it is expressed in an equation where we have those coefficients, and we can place our values inside. So where it is. So for example, we estimated those equations. Beta 1, beta 2, beta 3 are estimated. They are numbers. So we just place x and the x squared value and got the value of y. Just as a simple equation, mathematical expression. All right, next thing. What do we mean by linear regression model? We already answered that by answering the question why we need regression analysis. So regression analysis allows us to quantify the relationship, to estimate not qualitative but quantitative values, and using only mean value, we would ignore the information contained in other variables that could help us explain variations in dependent variable. And linear regression is just a linear model, linear relationship, which is expressed as an equation where the sum of the products of coefficients and the dependent variables is linear. All right. So let's have a break over here. All right, let's continue. Okay, so next thing we have to understand whether the models are linear regression models or not. So what can you say about reciprocal model? Is it linear or not linear? Is the model linear or not? Who can answer? The code was FD5IC6. Is this model linear or not?
No.
Why not? What we're caring for is the linearity in parameters. What are the parameters of the first reciprocal model? Beta 1 and beta 2. This is a linear combination. Beta 1 plus beta 2 times something we just don't care about. It's just a linear regression model.
So it's like a linear in parameter?
Yes. What about this one? Same logarithmic model. Is it linear or not? Let me make it over here. All right, same logarithmic model. Marine? Is it linear? Beta 1 plus beta 2. We don't care about next. Yes, it is linear. Nothing more. All right, next one. How about this? Yes, it is linear, semi-logarithmic. What about logarithmic or double logarithmic model?
No.
Why not?
Because of the body delta.
Yeah, because beta is changed with logarithm. Logarithm is non-linear function, and we change the parameter beta here, it is non-linear. Actually, we can make it linear by so-called changing the variable here. We could select the variable as alpha, for example, equals to natural log of beta. We can do so, but in this part, it is non-linear. Some of the models are linearizable. So this actually nonlinear model. It's considered to be nonlinear. What about the last logarithmic reciprocal? Is it linear? Is the model linear? No? Why not? Look, beta 1 is unchanged. Beta 2 is actually not the same. Beta 1 minus beta 2, beta 1 plus beta 2, we don't care. It's just a sign in front of the coefficient. Anything which forms linear combination is linear model. We don't care about x's. Don't care. We just look at the parameters. They are linear. They are not squared. They are not modified like here. So if we see linear parameters, it is linear model. So the single model which is non-linear is logarithmic here, where we can see natural log of beta 1. Guys who just came, please sign in. 35 IC 6. All right. Question number 7. Are the following models regression models? Why not? So let's consider. Again, we just check linearity. Let's have a look at the first regression model. So the first regression model is linear. Is it linear? Yes or not? No. Can you make it linear? So E is the exponent. Can you make A linear? How would you do that? To make it linear, we just need betas to be linearly placed. We have to extract them from the exponent. How to extract them from the exponent? What do we need to do? I can only write on this part of the board. All right, so here we have y equals exponent beta 1 plus beta 2 xi plus ui. All right, so we can see that the exponent can easily be trimmed or excluded by taking logarithms. Log yi equals to beta 1 plus beta 2 xi plus ui. We already seen this semi-logarithmic model, and we conclude that this semi-logarithmic model is linear in parameters. So the original function is also linear in parameters because it can easily be linearized. You can change to the simple transformation. Just estimate the natural log of yi, and it will be a linear model. What about this one? Have a minute of think. Can you make it linear? So can we make it the model yi equals 1 over 1 plus exponent, and the exponent just considers this thing, what we call z. Can you make this model linear? This one is z. Let's divide 1 over yi. I don't know what's happening with my markers, but it's not very good. Okay, 1 over yi minus 1 equals e to the power of z. Right? What is 1 here? Yi divided by yi, right? Equals to ez. Correct? Okay, if it's correct, then we can simply take the log equals to beta 1 plus beta 2 xi plus ui. You can see that the model is linear in parameters beta 1 and beta 2. This thing, 1 minus yi divided by yi, is actually so-called logit model. There are logit, probit models, part of regression models. So here's the logit function. 1 minus yi divided by yi equals to those linear parameters. All right? Okay. See? Is it linear?
Yes.
Definitely, it is linear. Betas are just unchanged. What about this one? Let me make a little bit smaller. Okay, D. What can you say here? What can you say here? You can see that there are linear part, beta 1, 0.75 minus beta 1. Okay, this is just this beta unchanged. But there is another beta, which under the sign of exponent. That's not good. If you can say the mix, so if those equations, all betas are the same, they just inside the exponents, both of them, but here are the mix. Some of them are not under the exponent, some of them under the exponent. So these are mixed types of equations, and they are non-linear. You cannot combine them to be linear. If you take the log of that function, yes, exponent will disappear, but beta 1 will be under logarithm. And under logarithm, that means non-linear. So this d is non-linear function. You cannot use linearization here. What about e? What about e? You can see that there is beta 1 plus beta 2 cubed xi plus ui. Is it linear? This one. What do you think? Is it a linear function or non-linear function in parameters? It is linear. Why do you think so? What's the difference between C, for example, and E? Just looking on beta 1 and beta 2. Looking on beta 1 and beta 2 cube. What is the difference? Can you make linear out of that function? The only thing to make it linear is just to change beta 2 somehow. How to change beta 2? Take the cubic root, but if you take the cubic root, you need to take the cubic root out of beta 1 as well. And beta 1 will become nonlinear. So if one part of beta is linear, one part nonlinear, one part, for example, logarithm, the other part is exponent, which are nonlinear. You cannot provide any change to make them linear, the function will be nonlinear. So for example, here we don't need to change anything. Here, beta 1 and beta 2, they are under the same function. So we can provide the reciprocal function, the logarithm, to take both of them out, and they will be linear. We cannot provide any function to make them linear here. Take the cubic root, b1 will be in the cubic root. Okay, non-linear. Okay. So hopefully you understand. Anything you just have a look, you look at the betas. We are only caring for linearity in parameters. So once again, here beta 1 is under logarithm, other beta is without logarithm. So that's why it is non-linear. The rest, beta 1, beta 2 the same, beta 1, beta 2 the same, and in here beta 1, beta 2, beta 1, beta 2. So all of those linear. All of those are linear. All right. Last question, and then we will move to Google Colab and start our practice. So the question is like that. Let me make it a little bit larger. So here's the regression line. Here are the points. Different points represent different regions: East Asia and the Pacific, Latin America and the Caribbean, with a lighter color, Middle East and North America, South Asia and Sub-Saharan Africa. So there is a mix of those values. The whole graph represents growth rates of real manufacturing wages and exports, 50 developing countries. So here is the average growth in real manufacturing wages, and here's average annual change in export to gross national product ratio. All right, so what is the question? What is the question here? You are given a scatter plot. What general conclusion do you draw from this diagram? So how actually can we analyze those types of diagrams? How can we analyze those diagrams? We look at axes. What do they mean? We have a look at average annual change in export to GNP ratio. So we can see that the relation is like that. Some of them are small, some of them here, some of them there. Significant variation inside those values. What else can we see? If the line represents the growth, so if the average annual change grows, will the average growth in real manufacturing be higher or not? So if it is low, the average growth is like that. If it's about 0, it's below. It's above here, it's over there. So to me, this linear regression is not perfect, and the more perfect relationship will be something like that, maybe exponential or quadratic relationship. But the question is, the question remains the same. Is it the population regression line or the resample regression line? Is it the population or a sample? What can you see? We're given the population. You have 50 developing countries, and the line is the population regression line here. What else can we see? What else can we see? Is this scatter plot reminding you anything about economic theory? Let's have a look. What does it mean? Export to GNP ratio. So that means the countries are trying to export more goods in terms of their national product. So for example, the gross national product of the country is $1 billion. The ratio of exports might be large, so the country produces something and places those goods to trade. It trades those goods outside. So this is exports. And the higher the exports, the more export-oriented country is, right? So it just shows that more export-oriented countries on average have more growth in real wages than less export-oriented countries. Why is that? Because we can see that if we move along this axis, those points tend to be higher. That means the average growth in real manufacturing is higher. So that's why actually in terms of economics, many developing countries, we are seeing this data for 50 developing countries during 1970s, 1980s. Those developing countries have followed an export-led growth policy. So they try to export more and earn more money, right? So that means they try to pursue this type of policy. So once again, the population regression line or sample regression line. I believe that the population regression line should be over here. It is the true relationship is quadratic. So if we suppose that we remove those line out of the graph and ask us to draw another figure, I'll draw like this, quadratic. That means if the true relationship is indeed quadratic, then this line represents the sample. So maybe this line is just based on the sample of those countries. But the true population regression might be different. All right? Okay, next thing, we try to open collab. Okay, and do you need me to open the previous week's file? Or we can start with this week's file? If you need, just let me know. So this fixed file is week 2. Right click, save link as, we save this file, and we will also need the datasets folder. We download them and extract here. This folder contains several tables. So for example, this is the table 1.2. Here's how it looks like. So there are some spaces, there is the name of the table, there is some information about what is happening there, and countries and the data inside, like that. So we are going to go to Collab and upload the file upload notebook, those week 2 econometrics notebook, and you should see it like this. All right, on the left hand side, let me make it a little bit larger. Oh yeah, it's here. All right, so 288 is enough. 288 is enough. Okay, on the left-hand side, you can see the folder, and you upload the unpacked files to the folder just by dragging and dropping them. Let's drag and drop those tables inside. All right. Okay. So here, let's start with 3 examples, and you'll have 2 tasks that you have to do on your own. Examples 1, 2, and 3, they involve tables 1.2, 1.3, 1.3, and 1.5. Actually, I don't know why we need table 1.4. It's inside 1.4. Okay, maybe we will need them later. Okay, let's start with example 1.1. Here's the data on CPI in 7 industrialized countries. From the given data, compute the inflation rate. For each country, plot what broad conclusions can you draw, and so on. So let's start with dealing with this kind of task. First of all, I suggest that we will need several packages to be loaded. And the first one is pandas to work with tables. We might also need NumPy package to work with arrays, and matplotlib package to draw plots. Matplotlib pyplot as PLT. All right, so we'll need those. Then we run the cell, and in the next cell we actually can start dealing with the task. I'm copying that in order for you to see what's happening. All right. Data will be called data, and our idea is to use pandas method for reading text and text is actually CSV or TXT here, we can see that those files are in their text documents, they're TXT format. CSV is called the comma-separated values. It also can be used to read text files. Here in read CSV, we need to specify the name of the file. The name of the file will be 1.2.txt like that. And then we just get the idea of what to expect. So for example, if I try to read the text file like this, what can I see? And I can see that actually kind of messed up with spaces, with everything. So we will need extra commands or extra parameters in this read CSV to make everything work perfect. So for example, we need to introduce the parameter of skip rows, because as we have seen, there are several rows. For example, I am opening like that. 1, 2, 3, 4, 5. 5 rows are actually not numbers. So let's introduce skip rows 5 and have a look what is happening. And you can see that it starts with 1973, then it places tabulation symbol. So the data is tabulated. Let's use the delim white space parameter set as true. We set that there are no header, true, and header is null, equals null. And have a look at what we obtain. So this actually looks all right. So it starts with year 1973 and have several columns. What should we introduce inside the data? Here the header is none, that means we deleted the header, but we still need to maintain columns. So data columns, dot columns, should be in the squared brackets, and we just copy the header, either from opening table 1.2 txt or opening it over here with double clicking and copying this Canada and so on from here. It really doesn't matter. So once we copy it, don't forget to place quotation marks and separate those values with commas. Alright, so it should be placed like that. The only thing that we are doing so is because there are not that many columns. If there are many columns, of course, we will need to read the specific row and transform them into column names. Okay, so where is our has has 7 elements? Hold on. Year, yeah, year. We also will need year. And then Canada. Okay, so now everything works perfect. Okay, so here we have read our data, and now we can answer questions. From the given data, compute the inflation rate for each country. To compute the inflation rate, we actually see that there are consumer price indices for those industrialized countries, and inflation rate has the formula. Let me place the formula for you. You don't need to type that. I'm just inflation rate at time t is the difference. The first one is CPI t minus CPI t minus 1 and CPI t minus 1. Okay, so here we are times 100, right? So this is the formula to calculate the inflation rates, and we're going to calculate them instantly. In order not to lose output of our data, we can print the data.head. Just see the first several rows. Next, let's have a copy of inflation data, for example. Inflation data will be the data.copy. And because we used pandas to read that PD read CSV method, the data appears to be pandas data frame. Pandas data frame allow us to select values using special method index location. So inflation data dot ilog in all the rows and starting from column 1 will be percentage change, of the same thing starting from column 1 dot PCT change times 100. So this is the formula which calculates our percentage change and calculating the inflation rate. And let's have a look at what inflation data actually calculates us. And we can see that it starts with 1974. 1973 contains not a number values. So in order to discard those values, we just use the drop NA function and print the inflation rate head. Print inflation data head. So here we are. This is the code that answers question A. All right, once you've done it, have a break. All right, let's continue. Next thing, after we have estimated the inflation rates for 7 countries, our second task, B, is to plot inflation rate. And I'm creating the code cell underneath. And I'm placing commentary mark in order not to distract anything. If we need to make the commentary in several lines, I'm just creating those commentary marks in several lines. Okay, so here we are trying to plot. As you noticed, we loaded package matplotlib and call it as plt. Now plt dot will contain functions that are needed to create figure and to plot necessary data. So plt.figure is the function that allows us to set the figure size, so how large will be our plot. And it is measured in inches actually, so it will be 14 horizontally and 8 vertically. Now we can see that our inflation data, when we printed our inflation data, it contained several columns. Each column corresponds to the country. So we are trying to iterate over countries. For country, country is actually a variable. I'm just trying to make it meaningful. So we can use for I in and then inflation data dot columns and we start with the first column. In Python, all iterations start with 0, so we skip the 0th column, which represents the year, and start with the country. And we place the column mark. When you see the for, when you see while, when you see if, so all these command words for cycles, when you press enter, you can see that there are several spaces. So by default in Python, we have to use 4 spaces indentation. And this indentation just corresponds to the code block. So for example, in R, we had to place 4, then we place something here, then we place the construct like that. It was in R. So we don't need to place any begin and end. We just place the column mark, hit enter, and automatically got 4 idents. If you see 2 idents, then you can change that in settings, I believe, with editor and indentation width in spaces. By default, it should be 4, not 2. Okay. All right. So for country and countries, we will add the plot, inflation data, copy inflation data, year, inflation data year, and inflation data country. This will be the iterator, right? The country itself is the iterator, inflation data country. And label will be country. All right, so now we created the plot. If we run the code, it should show us those lines. Now it's quite hard to distinguish between them, but let's modify the necessary parts of the plot. Here we specify the title. So we created several functions to specify the title, specify this legend, and specify Y label inflation rate and X label year. And in the end, we should see the plot with, which looks like that. Okay, let me remove this plot and open both chunks of code. So if you need, make a photo. All right. If you experience any problems, don't forget to load necessary packages. These are the import pandas, import numpy, import matplotlib. Those are necessary. Okay. I recommend you to save those notebooks and make some notes in order to just copy and paste the code. If you need to produce the plot, just copy the code and it'll be fine. All right, question number C. What broad conclusions can you draw about the inflation experience in the 7 countries? So that means we just need to have a look at those plots and try to sum up our observations. So first of all, we can see a general decline. Inflation rates generally show a declining trend across all countries, especially in the early 1980s. We can see how fast everything goes down in the end of 80s and immediately after 1980. This actually aligns with the global economic stabilization. In that period, in 1980s, everything was, the economy grew well, so inflation rates generally declined. What can we say about this huge volatility in 1975? The middle of 1970s actually was the so-called oil crisis, and there were harsh economic conditions, so this period satisfies this huge volatility. We actually can distinguish between countries. We can see country-specific trends. So for example, France, this red line is actually quite high. We can see that the United States is quite low. We can see how Germany behaved perfectly with very, very low inflation rate and stable inflation rate throughout the period. So country-specific trends can be given here. All right, next, which country inflation seems to be most variable? Can you offer any explanation? This type of questions involves calculation, so you don't just answer with what you see, but you have to provide some reasoning to calculate the parameter. What parameter should we calculate? What actual what formula will help us explain the variability, right? In statistics, what distinguishes variability? What is the measure of volatility? We can calculate standard deviation, for example, or variance. But standard deviation actually allows us to draw reasoning much better than variation. Standard deviation has to be def, let it be like that. So we are using inflation data dot log all rows and starting with the first column dot std. So it will provide 7 countries and 7 standard deviations for each of the countries. And you can see that there they are, printing those standard deviations. And after that, we can find the maximum standard deviation dot index maximum. Let's have a look. IDX max, and it shows us Italy. And we can include this information, print maximum volatility in, for example, Italy, with and here we place, for example, standard deviation dot max, just like that, for example. So the maximum volatility is in Italy with 6.29 units in inflation rate. The lowest in Germany, 1.87. Okay. So next, plot the inflation rate. Plot the inflation rate. We already plotted that, right? Versus United States. All right, okay. So those inflation rates versus United States inflation rate. All right, let's do that. So here I'm going to copy the previous code. I'm going to copy the previous code. But in E we are going to use the scatter plot instead of plot. Scatter. In the X we're going to use United States data. Label will be country, F country, in the curly brackets, versus US, like that. Now we have to distinguish what will be the countries to compare. And here are the countries to compare. Canada, France, Germany, Italy, Japan, and the United Kingdom. Okay, so we have to create array countries, for example, to compare. Call them like that. Don't forget to place quotation marks. Italy, Japan, and the United Kingdom. And we are going to iterate for country in countries to compare. And plot inflation rates. In X label there will be US inflation rate. Of other countries. Okay, so United Kingdom, it will be UK, I believe, 2 letters. Okay. So the code is like that. In order for us to easier interpret the plot, I suggest that we change it to quadratic, so figure size will be 8 times 8 in order to produce the square. Okay, and what can we say? What can we say about inflation rates and the behavior of the inflation rate in the sixth country versus US? First of all, we can see that there is a positive correlation. We can see that generally when the US inflation rate goes higher, the inflation rate in other countries also increases. All right, so positive correlation. Next, we can see different magnitudes. The magnitude of the inflation rates across, for example, Italy. For example, Italy, this one red dots, we can see those red dots are on top of US inflation rate. And Italy often has higher inflation rate compared to United States. Germany is green. We can see that those green are lower than United States. So Germany has lower rates. All right. So generally there is a positive correlation. There are some countries with lower. There are some countries with higher inflation rates. That's how we interpret. And let's have a look at F. That's what we just did. We commented on the behavior of the inflation rates. So once again, here's the code if you need. Make copies. And let's move on to the next example. Here again we will need to load data. Data is in table 1.3. Make sure that you have this data over here. We are going to use the previous code, just copy and paste in order to read. So here is how we read data from table 1.2. Copy and paste. Here we'll have the, for example, exchange data, X data, table 1.3. Again, I'm creating columns: Canada, France, Sweden, Switzerland, UK. In the previous 1.2 there were different countries, so make sure that you are using those values. Okay, Canada, France, comma Germany, comma Japan, comma Sweden, comma Switzerland, and UK, the last one. Alright, so here we have created data columns, X data columns. Don't forget, if you change your data, always don't forget to change your data all the way throughout that. Alright, make sure that it starts with 1977, table 1.3. It starts with 1977, 10633. Check that. If everything is correct, then you have read your data correctly. Two tasks: plot the exchange rates and
the dollar is set to appreciate, so let's compare after we plot everything. So copy what we plotted over here and try to modify. Country will be not the inflation rate but in the exchange data columns. Again, exchange data will be used here, here, and instead of inflation rate, we will just use the exchange rates. So, for example, okay, it will be like units of foreign currencies, units of foreign currency versus USD. The years actually are 1977 1998, like that. So what can we see here? We can see that the exchange rate of Japan? Japan, yes, is higher, and we cannot see anything meaningful in the rest of the countries. Obviously, there are some outliers, or the values in the Japan are much higher, and we can see that the Japan has 260, 270, and so on. We must change units of measurement. In order to do so, it's easier for us just to produce the graph in logarithms. So I'm just copying all the code, and I will produce the graph using the logarithm. NumPy log function, x data country in brackets. All right. So the single thing that I have changed is this NP log. Once we bring the data, now we can see, we can distinguish between different lines, and everything should be easy to consume. All right, so here are logs are introduced. Let's modify the title a little bit. Logs of exchange rates. Okay, so here this is just made for better visualization, but we can it can help us to discern the trends over time, because in the original plots, what could we say about the trends? Nothing. But in logs of exchange data, we actually see that they are stable, or they are declining, or they are not declining. First of all, linear trends. Log transformation helps us in identifying linear trends, which may correspond to exponential in original data. So if you see a line here, that is the same as exponent in the non-log form. And we can see that Japan's exchange rate shows a declining linear trend, indicating the exponential depreciation against the US dollar. We also see that the Germany, the green line, Germany and the France, this type of color, the logarithm of exchange rate stabilizes over time, right? So we can see that some stabilization. So the original exchange rate could be following a power law. Log transformation also prevents the volatility features. For example, Sweden, Switzerland, in 1980s and 1990s, we can see those ups and downs. What else? What can you say about United Kingdom? It also shows some stabilization over time. Okay, this is the question A.
And question B, the dollar is said to appreciate if it can buy more units of foreign currency. So the US dollar appreciates when it becomes more expensive. Depreciate if it buys fewer when it becomes cheap. So what can you find? What factors determine the appreciation or depreciation of a currency? What has been general behavior of US dollar? Whether it appreciates or depreciates. So first of all, we can see the factors that influence currency appreciation or depreciation. That might be interest rates. High interest rates offers larger returns and attracts foreign capital, and they cause currency appreciation. So more capital, more expensive the currency. There are some correlation between strong economic performance trends and currency appreciation. Countries that are politically stable generally have stronger currencies, and of course countries that exports more than imports will generally see an appreciation. So four main factors: interest rates, economic indicators, political stability, and trade balance. Now, we can see that those countries are European countries. They are politically stable, they are having good trade balance, but they might have different interest rates. Canada, of course, is not a European country, but still, and Japan. But they are developed and politically stable. So what can we say about the difference or the appreciation rate against Germany? Appreciation rate against Germany or against France, for example. What can we say about Canada? Canada is stable. Canada is stable. Germany, actually, the United States dollar depreciates, so it becomes weaker. Germany currency becomes stronger. The same goes with Japan. Japan currency becomes stronger than dollar, and currencies of United Kingdom or Sweden, yes, Sweden becomes cheaper. Swedish crowns becomes cheaper throughout that time. Okay. Next, what can we see? We haven't done anything with table 1.4, but let's do that. So table 1.4 actually contains only the single column of values. So let's plot this single column of values. Again, we just need to read the data. I'm copying this. And I'll show you how to read the data. Let it be M1 data, because our data involves seasonally adjusted M1 money supply. 1959, 1999, just like that. So let's read the data. M1 data PD read CSV 1.4. Let's comment that and let's print M1 data. And we can see that it starts with 139.74. Let's check whether it is correct or not. And we can see that the data starts with line number 6. So we actually need to skip less rows than 5. We skip only 3 rows instead of 5. And check how it prints, and we can see 138.89, which is correct. So every time, look in the data, check how it read. Check how it read. So for now, everything should be okay. And we have to create the column head. So instead of X data columns, we create M1 data dot columns and let it be M1. Just like that. Okay, now the data is called M1. What actually is important is that the time series data. The time series data needs us to create the year or the month. So this is the monthly data starting with January 1959, ending with September. What's important here? Time periods must be created as the range. PD data range. And this function needs us starting point and ending point. So start with 1959-01, like that, and end. And let's say that we accidentally used 1999-09, which is not correct. I'll tell you why a little bit later. And the frequency is monthly, just like that. And let's have a look. M1 data time period will be this newly created value, time periods. Start and frequency. Okay, so let's have a look, and we can see. All right, pandas have why no data range. Not data, date range, of course. So the date range works fine, and we can see at the error. The error says that line number 6 actually is wrong. Why it's wrong? We can have a look at the value error. Length for 88 is less than for 89. Why is that? The length of time periods has 488 values. We can see it over here, the shape. M1 data have shape 489. So that means the ending value must be 1 larger. In order to include the last observation, we have to increase into 1 point. Then the last value will be 1999-09. And 1999-10 won't be included. All right, now M1 data is okay. We can use it. And to plot, everything goes here by copying and pasting. But we do not need any for. We do not need any for loop. We also do not need any large value, just let it be 6 times 6. PLT plot M1 data as the X value will be time period. That's what we have created. And Y value will be just the M1. Another value that we have created over here. We do not need any label, but we can place the marker as necessary. So here will be table 1.4 gives us seasonally adjusted M1. Let us copy just like that. Year will be time period, and here will be M1 money supply. All right, and let's plot. As we can see, the graph which just shows how the money supply increases over time. Why this happens? Generally, money supply increases when the country needs in currency. When country needs currency, when it produces more. When GDP increases, the income increases, then more money is required. So here I made that example just in order for you to get the idea when you are dealing with time periods. Don't forget to use one extra observation in the end, and try to read your data by skipping appropriate number of rows. Always check how you start, how the data start, with which number, with which value. All right, what else? The final example that we need to make is example 1.3. We still have time to do that. Again, let's start with copying that. First of all, we need to plot impressions 1.5. We have to read the data 1.5. Let us call the data as advertisement expenditures data. I believe skip rows 5 will be okay for that. Let's check what we see in table 1.5. We can see two columns. The first one will be impression, and the second will be expenditures. ADEXP. All right, here, like that. We do not need time periods. I think this is not important. So print what we see. Impression and advertisement expenditures 32.1, 50.1. Check 32.1, 50.1. Yes, the data read correctly. And plot the data. Let it be 8 times 8 figure. Advertisement expenditures data here and there. On the x-axis there will be expenditures at the x, and on the y-axis there will be impressions. Here will be the impact. Right, advertisement expenditures here, million USD. And here impressions again in millions. In a week. So why this thing actually produces some strange picture? Because we're using PLT plot. In order to use proper thing, we need to scatter. PLT.scatter. Just like that. So the data points are dispersed. We can see that there is a high variability in the relationship. Looking at the points, what we can see, there are actually there isn't clear trend. There isn't a strong linear trend between the variables. Some firms with lower advertisement expenditure, they can have higher impressions. Those with higher advertisement expenditures have twice lower than that. So, it's quite hard to distinguish whether advertisement expenditure actually brings impressions or not. There are a few data points with very, very high advertisement expenditures, but relatively lower impressions. So maybe those points are actually outliers. So if we consider those points as outliers, then we can see that the trend will be like that, and the regression will be like that. But if we leave those points here, then the regression might be logarithmic, just placing like that. Okay. What can you say about the nature of the relationship? And looking at the graph, do you think it pays to advertise? So I think, first of all, that quality should be on the first place. Quality over quantity. It's not just the amount spent, but how you spend those money to contribute to impressions. And what can you say about the nature of the relationship? I don't know, maybe it's just the event specific something. Actually, advertisement is not a guaranteed method of generating impressions, but it plays a role. And maybe the platform, maybe timing could be pivotal here. What we can see through those sample, as I have said, the relationship is logarithmic. It's over here, produced nonlinear. But if we subtract or divide those couple of points and separate, let's say that we separated over here about $60 million US expenditure, and look at those 1, 2, 3, 4, 5 points. What can we say? We can see that the relationship is actually negatively sloped. So the more you spend, the less impressions you've got. So that's an addition to considering those values as the outliers, actually. And in the end, we cannot say anything particular about the relationship. Too few points to consider, but again, regression can help us identify the pattern, especially if we spend not that much. Below 60, below $50 million, it might be a good option to just use the linear regression. All right, so this is it. Try tasks 1 and 2 at home. Don't forget to load those tables. Here, don't forget to run these 3 lines, which loads necessary libraries and functions in your PD, NP, and PLT variables. And I think that's it. Thanks for coming.